Larson, director of the Pioneers of Science and Technology Videotape Project. About 300 years ago, Isaac Newton wrote that we make progress only by standing on the shoulders of giants. This project is dedicated to preserving on videotape some of the wisdom of those contemporary giants and pioneers who during the past half-century were responsible for the advances in science and technology which have revolutionized our lives. This interview gives us an insight into the contribution which these individuals have made to our civilization. We now join the interview in progress.
I feel a little humble about claiming that I have made any important contributions, but I certainly have had a very interesting life because I became interested in radio. In the early days, we didn't have any such thing as electronics. It was radio and wireless, as perhaps you recall. And I became interested in radio when I was still in grade school, as a matter of fact. I was born and brought up in Pueblo, Colorado, and somehow I was intrigued with the development because, as you recall, radio broadcasting began to become established in the early 1920s.
Yes,
and,
I remember that very well.
I was born in 1912, so I was about 10 years old when some of these radio broadcasting stations became established. And I think the first experience, my father bought me a vacuum tube, and I hooked it up on the dining room table, and the first station we got was WHO in Des Moines, Iowa, and that was about 1922 or 23 when I was 10 or 11 years old. So my interest in the electronics field began early, and I really stayed with it. I became a radio amateur while I was still in high school, and as you know, radio amateurs were involved in sort of the fringes of the development of the radio industry, and actually made very many contributions over the years, and I still now and then run into someone around the world that I talked to when I was a radio amateur back in my school days in Pueblo, Colorado. I guess the most important factor that influenced the course of my career was the fact that I came to Stanford University in 1930 and took a course in what was then electrical engineering. Dr. Fred Terman had come to Stanford a few years earlier. He had graduated from Stanford, and I think he got his doctorate degree at MIT in chemical engineering. But he had also been a radio amateur, and he became interested in radio engineering and wrote what became, I think most people would say, was the first and most important textbook in the field of radio engineering, which was published in the 1930s. And it was, I think, studied by almost every student of radio engineering and electronics in the period from the mid-1930s on up to about 1950.
Because I think I have a copy of 1940 edition.
Well, I think anyone who ever had any involvement in radio and electronics and through that period had that book. Fred Terman was a very interesting person, and I was very fortunate to have the opportunity to become acquainted with him. He stopped me in the hall one time while I was a junior, and I used to get over to his laboratory because he had an amateur radio station at Stanford, and I was involved in working with that, and it was through that involvement that Dr. Terman came to know about me. And it turns out that he had realized I was interested in radio, and I also had taken most of the other courses necessary in electrical engineering. And so he offered to let me take his graduate course in radio engineering, which was based on that textbook. And I was the first one to first undergraduate that was allowed to take that course. And so during my senior year, I attended his graduate course, and that, of course, really reinforced my commitment to want to spend my career in the field of radio engineering and electronics.
I'm very happy to hear you mention Dr. Terman, because I know my son has said that without Dr. Terman, there probably might not be a Silicon Valley. Valley today.
He was very influential, and I might tell you a little bit about that, because in the course of his interest in radio engineering, he became acquainted with almost all of the people who'd been pioneering in the industry, many of whom were right around this area, because there was some early work done by some Stanford graduates going clear back to the beginning of the century. And the Federal Telegraph Company was established here in Palo Alto based on the Poulsen arc patents, which were obtained from Denmark by a Stanford graduate in about 1905, I believe. And then Dr. DeForest invented the vacuum tube here in Palo Alto in 1908. And
well, I had forgotten that originated in Palo Alto.
Oh, yeah. Well, and then Dr. Fritz Colster developed the radio direction finder in the 1920s. He lived in Palo Alto. And the Jensen loudspeaker was the first dynamic loudspeaker, and that company was established in Oakland.
Yeah, I think I have an old model of the Jensen still on my shelf.
And then Philo Farnsworth, at that time, was doing his work on his picture tube for television.
Oh, yes.
And in the course of this study with Dr. Terman in radio engineering, he arranged visits for his students to go around and visit these companies. And this was a very intriguing experience, because we visited Charlie Litton, who had started a company up in Redwood City to build vacuum tubes, but he ended up concentrating his work on vacuum tube manufacturing machinery, glass-blowing lathes, and so forth.
I remember the famous Litton glass-blowing lathes. In fact, I used one.
That was his contribution. And we visited Farnsworth's research project. It was up in San Francisco at the time. And this was during the Depression. And as we came along toward graduation in the spring of 1984, there's some concern about whether we were going to have a job. And Bill Hewlett and I had become friends as freshmen at Stanford, because we were both taking the same engineering courses, and so we've been in courses together for the 3.5 years or so.
Was Mr. Hewlett also involved in amateur radio?
No, Bill Hewlett was not involved in amateur radio. As a matter of fact, he had very little interest in radio until we got acquainted. He'd been interested in other things. But he developed his interest, again, really under the influence of Dr. Terman. But in any case, Bill and I had talked about the possibility of starting a company ourselves. We talked about this in the fall of 1933 when I was first taking these courses here. And Fred gave us a little encouragement, because he said, well, look, a lot of these people who started these companies here that have been quite successful didn't have very much formal education in radio engineering, and he said you and Bill have probably had more formal education, and there's no reason why you couldn't be more successful. Well, we weren't quite sure, but in any case, we were fully committed to the proposition that if we couldn't get didn't get a job that was satisfactory, that we'd undertake to do this ourselves. I was fortunate enough to get an offer to go to work for the General Electric Company, and being one of the very few jobs that was available in those days, it was too much of a temptation for me to give that up. So I agreed to take that job and went back to Schenectady, New York in the spring of 1935.
Yes, as a matter of fact, I went through the same Depression years, and there were about 100 applications for every job.
Oh, yes. Well, so I felt quite fortunate to be able to get a job with General Electric, and I think they hired 200 or 300 college graduates at that time from all over the country. And so I went back to Schenectady, and one interesting observation I made about that, when I got back to General Electric, my advisors recommended very strongly that I not get involved in electronics. They didn't think there was going to be any future in electronics, and they thought if I was going to be have a successful career in electrical engineering, I ought to concentrate in power generation or motors and some of those things. Well, I didn't agree with them, and so I went around myself and found an opportunity in the vacuum tube engineering department. It turned out that the advisors would help you get a location that you might be interested in, but you could also go around yourself and find something to do, which I was able to do. And so I spent most of my time, I remained there until 1938, in the vacuum tube engineering department, and we were working on mercury vapor rectifiers and ignitrons. But it was a very interesting experience because this vacuum tube engineering group was located in the same building as our main research laboratory there at Schenectady, New York. So I had a chance to be exposed to a good many distinguished scientists and people working on interesting things. So I had a little benefit of that acquaintance.
Yes, I believe that Coolidge wasn't Coolidge with the General Electric Company.
There was Hall and Coolidge and Langmuir.
Oh, and Langmuir, of course.
All made very important contributions in the theory of vacuum tubes. And General Electric was involved in the manufacture of some radio-type vacuum tubes, and they were making some large water-cooled anode tubes and transmitting tubes there at the department. But during this period, Fred Terman kept in touch with me, and as a matter of fact, he would quite often travel to the east and visit his former students, and a good many of his former students had jobs in the various electronic industries there, a number of them at Bell Labs, at RCA, and there were several at General Electric. Bill Hewlett decided to do some graduate work, so he came out to MIT, and several times Bill and I would get together. We'd go skiing together, and sometimes he would come over, and so we continued some discussion about this idea of eventually starting our own company during this interim period. In I got married in 1938. Young lady that I'd met at Stanford, and in those days I couldn't afford to come back to San Francisco to get married, so she got on the train all by herself and came out to Schenectady, and we got married in the spring of that year. In the summer of 1938, Fred Terman worked out a research opportunity for me to come back to Stanford. And he recommended that I do this and take some additional work, and he said that the combination of what I'd done at General Electric and I did a little graduate work at the University of Colorado, he said that I could get my master's degree, my engineer's degree. It was a double E degree in 1 year of residence instead of the usual 2 years of residence. And so we arranged to come back, and I had a very interesting project to work on an idea that Russ Varian had, which was a way of hopefully reducing the grid loss in a triode at high frequencies. And Fred Terman had arranged so that I could do this work up at Charlie Litton's laboratory, because it involved making one of these tubes to see whether it would work or not.
Yes, that's amazing because it was just about that time when the need for high frequencies was beginning to develop.
Well, that's right. And of course, the work on the klystron was being done over the physics department at Stanford, and there was a recognition that microwave would be very important for radar, and this was already known, and there was work being done in various areas. So there's quite a bit of emphasis on the development of better high-frequency technology at that time. Well, in any case, I took some courses, and Bill had found an apartment down on Edison Avenue, actually still there, with a garage, and so we set up a little shop in this garage, and we'd go to class in the morning, and we'd do some work in the garage, and trying to develop some things for our potential business. And then after dinner, I would go up and work in Charlie Litton's laboratory. And this worked out fine because he felt it was a waste of time to spend too much time in the office during the day. He said it was a waste of time with phone calls and so forth, so he wouldn't get started until maybe the middle of the day. But he'd work until 2 or 3 o'clock in the morning. And so I would go up there and quite often work until midnight or 1 o'clock, and I was young enough then I could keep up with all of these things.
Yeah, well, that's a fascinating story because that was such an important development. The development and the invention and so forth came at about the right time in history.
Well, it's just quite often a matter of luck that you happen to be in the right place at the right time, and I think that Bill Hewlett and I just happened to be involved in this industry at a time when it was really beginning to take off. And well, in any case, Bill had developed a new kind of an audio oscillator in his laboratory work over at Stanford. Fred let him continue some work over there even after he was completed his studies, just to sort of help out a little bit. And they had a very interesting group of people, and they were working primarily on ideas of applying the feedback principle to various applications. Feedback had been invented, brought out by Bell Labs people, I think about 1928, but it usually takes a little while for these new ideas to become known and to become utilized. So in 1938, they were still talking about how to utilize this feedback principle 10 years after it had been invented, and it was really about that time a lot of practical applications were discovered. Well, in any case, we built one of these oscillator models around Bill's ideas, and he took it up to the IRE meeting in Portland in the fall of 1938, and it received quite good acceptance. A lot of people were interested in it. So, with Fred's encouragement, we decided that we would use that to try and start our business. And so I still recall it was around Christmas time. We had this audio oscillator in the living room there. We took some pictures of it and wrote up some sales specifications. And Fred Terman had given us a list of some potential customers, and we'd got lists from a few other customers. And right after the first of the year, we sent out these letters offering this audio oscillator to a number of people.
Yes, as I remember, at that time, the ordinary audio oscillators were very cumbersome and not very satisfactory.
Well, they used the beat frequency principle, and the oscillator that was a standard was one made by General Radio. It cost about $500. It was a big machine and was not very stable at low frequencies. And this circuit that Bill devised, we made for less than $100. And in many ways, it performed better than the General Radio.
Yeah.
So it was a real good contribution. Well, in any case, shortly after we sent these letters out, we got some orders back, including some of those checks with them for the products. So that's really what got us started. And by the end of that spring term, I had to make a choice of whether to go back to General Electric or not, because I had been given a leave of absence. And General Electric was, at that time, in the spring of 1939, beginning to be involved in a little bit of defense work, and they realized that there was some important things to be done. So Mr. White, who had been the boss of the department, wrote me a letter encouraging me to come back, but I decided that we'd stay and make a run for it, which we did. So that's really how we got started. Now, Bill and I decided about that time that it would be desirable for us to have several products that were complementary. Obviously, if you make a sales call on a customer, if you have 2 or 3 things to sell, it would be better. And beside that, an audio oscillator was used with 2 or 3 other kinds of instruments to make the measurements you wanted to make, which would be the frequency response and the distortion that was generated by the equipment you're testing. So we proceeded to develop some equipment which would analyze the waveform distortion, including a harmonic wave analyzer that used the feedback principle, and then subsequently a vacuum tube voltmeter and some attenuators and so forth, so that we then developed a package of equipment that a laboratory or factory could use to measure their audio equipment they were making. And this rather limited product line had gotten a fairly good acceptance by within a year or so after we got started. And we had a few instruments that became quite important in the defense effort, so our business began to pick up relatively quite well at that time. Bill Hewlett had a reserve officer's commission in the Signal Corps, so he was called to active duty. And in fact, he was called before Pearl Harbor, and I was able to get in touch with his boss and convince him that Bill had an important job to do back in Palo Alto, and they let him come back. But then Pearl Harbor came along, and he had to go back to the service. So I continued to run the company for the next 2 or 3 years while Bill was away.
So you were able to furnish many of these instruments for the defense effort then?
Yes. Well, as a matter of fact, there was a great deal of concern in Washington as to whether or not there was going to be an adequate number of instruments to support the defense effort. And I was invited to become a member of the advisory committee to the Department of Defense. I think it was a War Production Board related activity. And the interesting story that I've often told about that, I became quite disillusioned about the ability of the federal government to know what's going on as a result of that experience, because they invited a number of us to come back there, and they said they had a list of the quantities of various kinds of instruments that they thought that they were going to need, and what would have to be done to get the industry to gear up and manufacture this. Well, we all looked at this list and all expressed the same amazement, because we were already producing much more in every category than they had on the list.
Oh, yes.
And so they finally decided that the best way to handle this was to recognize that the instrument industry was important, and that they would provide us with the critical materials with some priority, and then we could build whatever quantities were needed by the industry. So it worked out to be a very satisfactory arrangement. And our products were originally involved in such things as, well, the proximity fuse production line used our audio oscillators and part of it, and we supplied a lot of our audio equipment to various aspects of the defense industry. But we also became involved in some microwave work at that time. I had called on the Naval Research Laboratory a number of times to sell our products, and became acquainted with some of the engineers and scientists there. They had been doing some very interesting work in the development of microwave signal generators, and we worked out an arrangement with them where we made some of these microwave signal generators, and as a result, we began to build up some expertise in microwave measurement work.
Yes. What frequencies did that cover? At that
well,
time?
They started out at the 3 gigahertz range, but there was some interest in all the way from 1,000 megacycles, but there was interest clear up to the X-band at that time.
Oh, yes.
And we eventually did some work in the whole area, and it was a result of those initial contacts that we built up quite a little capability in the microwave field. And it was an interesting development after the war in this regard, because the General Radio Company had been the main competitor. They were the big business in this little field we were involved in, and they had done some work in microwave instrumentation, but for some reason they came to the conclusion there wasn't going to be any future for microwaves after the war, and they left their work down, and we were convinced that microwaves were going to be increasingly important. So we were able to hire half a dozen very capable people who had been involved in instrument work during the war effort. And although our business was a little uncertain in 1946 and 47, we were fortunate enough to get a good group of people together and to continue the development of some pretty good work in the field of electronic instrumentation.
Yes, well, really the future of the aviation industry, I guess, was critically dependent on good microwave and radar equipment.
Well, it turned out that electronics was important in a number of industries, and avionics. We start, of course, with communication, which had been developed very well along the line by that time, and then radar, and then navigation. So that, as you know, electronics is a very important element of all kinds of avionics work. But our company we were still quite small. In fact, we had reached about a total of 200 people during the war, and it was 1949 and 1950 before we got back up to that level of activity again, a couple $1 million a year. So it wasn't any large endeavor. But fortunately, we had done some good work in building up a line of solid measuring instruments that, in many cases, were as good, in many cases better than anyone else had. So as the electronics industry began to pick up in the 1950s, Korea had some impact on it. We were in a good position to expand with it, and our expansion really started in the early 1950s when we saw the company grow quite rapidly from that period on.
What were some of those instruments that you brought on the market? Of course, I can remember that your oscilloscopes are so famous, but are there others?
Well, as a matter of fact, our contribution in oscilloscopes wasn't all that good. So we had already made some good contribution in the audio field, which I described, and we continued work in that, and we continued some development of some microwave equipment, and we had some good microwave signal generators that were broadband and very useful for anyone doing work in the microwave field, and I think without any question we had developed the best line of microwave signal generators that was available at that time. Although there was competition, and you always had to run to keep ahead of that. But we started another program which became very important, and that was equipment that would measure frequency using digital techniques, so that you get a digital frequency meter and read frequency directly instead of having to measure it by indirect means. This came about in a rather interesting way. We sponsored some research over at Stanford of two young people to look into the possibility of making some instruments for nuclear work and counters for nuclear measurement. And they came up with some technology which would enable counters to operate at a 10 megacycle rate and measure with 1 cycle accuracy at that point. And we concluded that it would be a much better opportunity to make a frequency meter that would be direct reading up to 10 megacycles rather than bother with the nuclear field. And so we came out with the first frequency counter that would give you a direct reading of frequency input up to 10 megacycles.
And then you used digital techniques.
They used digital techniques, and so this would actually read out the frequency in the numbers directly. With the accuracy, of course, was determined by the accuracy of the time standard that you used, because you had to count the number of cycles for a precise period and measure them in that way. But that was a very important contribution because it made the frequency measurements much more accurate than could be done before with simple means, and much more rapid. These first high frequency counters we made were fairly large and complex, and they weren't too reliable, but they were so useful that they were very well accepted, even though the reliability wasn't very good in the early stages. Then we had concluded at the very early stages of our activity that we didn't want to simply be a Me Too kind of a business. We wanted to try and find ways in which we could make a real contribution to the field we were in. And one contribution we made that was a very important one was to make a vacuum tube voltmeter that could read higher frequencies. And the limitations on the high top frequency range you could use with the techniques which is simply use a diode to rectify the alternating current and then measure the DC as a measure of the amplitude of the alternating current. These were limited by the transit time of the electron flow in the diodes. And these were vacuum tube diodes that were used. Crystals had been used to some extent at that time as detectors and mixers for microwave work, but we weren't able to get the stability and accuracy with the crystal detector that you'd like to have, and so we had IMAC develop a special diode for us that was very closely spaced, and this Model 410, I guess is the number of it, was a high-frequency voltmeter that would go up to 700 megacycles, which was much better than anybody.
Oh, yeah, that's a tremendous jump in usefulness.
And so that became a very good instrument. And then we, during the 1950s, we made quite a few good contributions. As a result of our interest in this frequency measurement, we did a good deal of work on development of accurate quartz crystal controlled frequency standards. And we brought in a young man out from Colorado named Don Hammond, who was one of the outstanding people in the country in working with quartz crystals. And we were able to develop more accurate and less costly crystal frequency standards. And then Don and his team did some other very interesting things. They, in making a frequency standard, you want to cut the crystal so that the frequency does not change with temperature. and you do that by cutting it at a certain axis in relation to its crystal structure. You can also find cuts where the frequency change will be maximized with temperature, and so from that we devised a way of using a quartz crystal as a quartz thermometer. And it turned out that this provided a very precise measurement of temperature, and so we developed a quartz thermometer using this crystal technology that we developed originally for the ultimate purpose. And a little later on, we designed one a quartz device that would be could be utilized to measure pressure, and we're still making those, and they have a very important capability. They can measure pressures up to about 10,000 psi with a resolution of about 1 psi. And so you can actually put one of these down a few thousand feet below the surface of the ocean and measure the barometric pressure at the surface with them.
That's amazing. Of course, the accurate measurement of pressure and temperature is a very useful thing in so many fields.
Well, these are being used now primarily in the oil exploration industry, where they want to measure temperature in these deep holes, and we make a special model of that that's used for that purpose. Then, as we began to round out our line of instrumentation, and what we tried to do was to develop a broad line of what we call general purpose electronic instruments that anybody doing electronics would need to have. We were quite successful in doing this, partly because we had concentrated on the field of instrumentation from the very beginning, and as a result, we knew a little bit about the business. And we also decided, as I've indicated, that we wanted to try and make some kind of a contribution to do something better. And the combination of these things made it possible for us to get a broad line of these general purpose instruments in production by the end of the 1950s. At that time, we began to look around a little bit to see what other things might be done with some of the technology that we developed, and we concluded that some of this technology would be useful in medical instrumentation, and we finally decided to acquire a company called the Sanborn Company, located in Waltham, Massachusetts. They had been the pioneers in electrocardiograph, and that was sort of the pioneer instrument in electronic applications to medical things. And Bill Hewitt had kind of a special interest in medical instruments. First place, his father had been a doctor, so he had been exposed to the medical profession to some extent. And he'd also done some work for some of the doctors here in Palo Alto. In fact, one of the projects we worked on in the early months when I came back here, he'd been working on this before, was an electroencephalograph, which is an instrument to measure electrical waves in the brain. So this field was one that we had an interest in, and by acquiring the Sanborn Company, this gave us another product line and opportunity to apply some of our technology. And then a little later on, we also concluded that some of the things that we were doing could be useful in making measurements in analytical chemistry. And there had been already a number of instruments developed. Beckman had been doing some work in that field. And the area of gas chromatography became quite important in the early 1960s, and we acquired a company that was in Avondale, Pennsylvania, just outside of Wilmington, where these folks had done the work in the DuPont laboratories and had established a small company to make gas chromatographs.
Yes, well, that field of application of instruments to those fields of chromatography and analytical fields that revolutionized analysis, both medical and chemical.
Well, as a matter of fact, there have been tremendous progress in this area, and we've had the opportunity to be among the people at the forefront of this field. One of the combinations that has been particularly effective is the use of a mass spectrometer in combination with a gas chromatograph. And these instruments make it possible to measure various chemicals in very small quantities, parts per million, and in some cases even parts per billion. And I've often commented recently that we had a lot to do with all this environmental business because they couldn't measure any of these things 20 or 30 years ago, and so they didn't worry about them because they didn't know about them.
Yes, I guess sometimes we might even perhaps wonder whether some of these things are a mixed blessing.
Well, I think that's quite right. But in any case, the instruments that our company developed did make a very important contribution in that field of knowing more about what's in the environment around us, and this includes both air quality and water quality, and matter of fact, our instruments are being used in the Olympic Games to check the athletes to see whether they're using drugs or not, and so our instruments determine whether the athletes are qualified or not in the Olympic Games in Los Angeles next year. And then we were in Moscow with our equipment the last time.
Oh, yes.
So we've had the opportunity in this course to concentrate on the field of trying to make better instruments using electronic technology, and it's been a very exciting business because although none of these are tremendously widely known breakthroughs in themselves, they have, I think, made useful contributions to a lot of scientific progress during the last 20 or 30 years.
Yes, well, of course, instrumentation, all the way from the invention of the microscope, the science builds on instrumentation, and the whole field of DNA and unraveling of the large molecules depends on these instruments that were available.
Well, there's been a tremendous amount of progress in this field. Now, as we saw this field expanding in the early 1960s, it looked as though there would be an opportunity to combine digital computer technology with instrumentation technology. And this was an area we became interested in the early 1960s, and we concluded that it was going to be very important to have computers work with instruments. And there were two reasons we saw this as being important. One of them was that you'd like to automate these measurements, both in terms of deciding what you wanted to measure and in analyzing the data so that it gave you the data in a form that you wanted it, which isn't always the case in the output of an instrument. And so we saw this business of combining instruments and computers into an overall measurement system as a trend of the future, and indeed it has become a trend of the future. And this makes it possible to make instruments which can do these things automatically. They can do it more consistently, and with less manpower, quite often at lower costs, and also much more rapidly. There's another interesting thing that came from this work of joining computers and instruments. It's never possible to make an instrument that is entirely free of all errors. You can minimize the errors, but you can never get that last little error out of the picture. And our customers, of course, always wanted instruments to be more accurate than the thing they were trying to make, so they'd have some margin of safety in the measurements they were making. And we worked very hard to try and design our instruments to minimize the errors and to take advantage of this. It turned out that by combining computers with instruments, you could in many cases calibrate the errors out of the instrument, or in a sense you could measure the errors with a computer, and then when you're making actual measurements, you could correct those errors and come out with a much more accurate answer than you could without a computer.
Yes, well that had tremendous application. Was that what was the name of that computer? Was that any relation to the HP? What was it? HP 80 or?
Well,
that come later.
That came later. Yes. This was the work I'm referring to now. It was strictly in relation to conventional digital computers.
Oh yes.
We looked at the possibility of acquiring a small computer company. We finally decided to develop our own computers, and we began in the middle of the 1960s to do that. And they were designed originally to work with our instruments for the reasons that I've indicated. Again, something happened that was really just a matter of luck. We had looked a little bit at what was being done in the electronic calculator business, but in fact I visited a company in the eastern part of the country one time and looked at what they were doing. It didn't look as though it had very much promise, so we didn't do anything about it. But about 1967, a young man came in to see us. He'd been working for the SCM company over here. In those days, as you may recall, calculators were all mechanical.
Oh yes,
a very sophisticated mechanical calculator, but there were no electronic calculators at that time. He said he had an idea how to make an electronic calculator. That he'd shown it to his boss, and they weren't interested in it, and wanted to know whether we'd be interested in it. And Bill Hewlett and Barney Oliver, who was our chief scientist in effect at that time, were both very good mathematicians in their own right, and they got quite intrigued with this idea that Tom Osborne came in, and so we agreed to take this on and design this electronic calculator. We put a very good team of people on it, and it turned out that Tom Osborne did have some good ideas. And we made some basic decisions as to how we would go ahead with this development. Integrated circuits were just beginning to become known and become utilized to a limited extent. Most of the electronic work still used the discrete components, discrete transistors and resistors and capacitors and so forth. We decided that to be sure about getting the circuitry to work right, we'd use discrete components. This device needed a read-only memory, and we decided the way to make that read-only memory was with a 9-layer printed circuit board. And to do that with the technique at the time required a circuit board of about a foot square. And we've been using what were called Nixie tubes as readouts. They were little tubes in which the wires would glow and make the numbers. So you could make the numbers from 0 to 9 with these, and therefore get a numerical readout. So we designed this calculator using that technology, and it turned out to be about the size of an ordinary typewriter, a little bit bigger maybe. But it had some extremely useful characteristics. It essentially had all of the transcendental functions that you have used on a slide rule in those days. It also had some programmability. And it immediately became a very, very popular instrument. We sold a great many of these. I remember the timing because I left the company in the fall of 1968 to go back to Washington, and I had one of these calculators with me that I kept and sometimes used in the work I was doing there. This then enabled us to develop a group of people with some capability in the electronic calculator field, which was similar but still not identical to what we had been doing and intending to do in the computer business. We continued both of these things, and in the interim while I was away, it turned out that large-scale integrated circuit work became quite practical. Read-only memories could be put on a little chip instead of a foot-square board, and you could also put all the other circuitry needed for a calculator in a chip or two. And we had been doing here in our own laboratories a good deal of basic work on light-emitting diodes. We thought this would be a very useful technology, and we had people in the laboratory who could make very good light-emitting diodes, little alphanumeric presentation. We couldn't get people in our division to use these. They liked the old Nixie tubes. They were bigger and they were used to them. But in any case, our work on light-emitting diodes had come along, so Bill Hewlett got all the team on this calculator group together and said, now I want you to take that calculator, it's the size of a typewriter, and redesign it so you can put it in your shirt pocket. And that was the genesis of the Model 35, which came out in 1972.
Oh, yes.
And that was really, I think, a very important contribution to the whole field of technology, because it provided a very, very precise calculator that you could essentially replace the old slide rule. There was no need for a slide rule anymore. You had one that would give you the digital accuracy, extremely good accuracy by comparison, and it became sort of the standard of everyone. Well, as you know, we've continued our work in calculators and computers, and our company now has a larger share of our total business in the field of digital data processing of one sort and another, including a line of computers and peripherals and calculators. These are still used extensively in conjunction with our instruments, and we are still continuing to develop newer and better electronic instruments. We introduced a new network analyzer just this year, and in all kinds of engineering work in electronics, you want to measure the characteristics of a network, or interconnection of transmission devices that will transmit signals in various ways. And used to do this by making simple impedance measurements, and in microwave work you use standing wave indicators and measured the standing wave and then translated that back to what it meant in terms of the energy transmission and so forth.
Yes, well, network analysis is very, very laborious.
It's very laborious and of limited accuracy, yet that was the way you had to do it in the early days of microwave measurement. Well, we developed some techniques. I think some of the basic work came out of Stanford, where you could measure the network in terms of its impedance and its transmission characteristics in a more straightforward way. And the latest instrument we brought out enabled you to do this from very low frequencies to very high frequencies. It has a lot of little mini-computer chips built in, so you get not only an extremely wide range of measurement, but extremely high accuracy. And this instrument is, in a sense, kind of the result of many years of research and development and experience in this field. And I'm needless to say very pleased that our people are still taking a very leadership position in bringing out better instruments in what was our traditional field that Bill and I started back in 1939.
Well, actually, each one of these built on your previous experience. And
well, yes, you see, you get a synergism out of this. What you're doing is you're continually trying to make every instrument you have in your line better. Now, you can't always do this because maybe you're at the limit of technology, so you're kind of at a standstill for a while, but every now and then some new idea comes along and enables you to do a little better job, and so it's been a very exciting business to kind of find ways in which to develop and manufacture and make available these instruments. And as you know, our company's total business this coming year will probably be in excess of $6 billion. We have some 80,000 people in the company today, but in a sense, we're still doing the same kinds of things that we started to do from the very beginning. And so it's been a very satisfying experience from that standpoint. We've been able to start some work in an important field and see it keep going. And I'm confident that the people working in the company are going to continue for a long time to make contributions and stay out ahead of the field, even though Bill and I are no longer able to be active anymore.
Well, I was noticing that when you read the technical journals, every once in a while a new Hewlett Packard instrument will come out, but just in I think yesterday or the day before was the announcement of the new type of printer, which embodies several new principles, which are built on your other work in the past.
Well, that's what we're trying to do, and obviously, if you can do something the other fellow can't do, you have a considerable advantage. But also, there's a lot of satisfaction in being able to make these kind of contributions, and our people are very enthusiastic. The development people are very enthusiastic because they know that they are able to make some important contributions, and we try, of course, to give them a good deal of recognition and encouragement for what they're doing. But the level of our activities is quite high. We're spending in excess of $500 million a year on developing new products. And that means we come out with a new product almost every day somewhere in the company. So it's a very significant effort that's been built up over the years.
Yes, that's double or treble the average research and development expenditures of the average industry.
Well, I think in terms of total dollars spent research, we're I think the third largest in the electronic industry after IBM and Bell Labs. And then of all industry, I think we're something like 13th largest in the country. And it's really the lifeblood of our business, and it's what Hewlett Packard has been all about.
Well, that's a fascinating story of the development of all these instruments, which really have advanced science and technology, and without which the whole business would be completely different today.
Well, of course, as I said in the beginning, we were lucky to have been sort of at the foundations of this whole electronics business that's developed over this last 40 years. Has been the real development.
Yeah.
I'm talking about this one little story I like to tell about myself. When I was at Stanford, I took a course in American history, and I had an opportunity to do a sort of a special studies work, and I studied the westward movement of people across the country from the early days in our history. And I remember thinking when I was a junior that I'd been born 100 years too late, that all the opportunities in the future had been gone, and I was very unhappy that there wasn't any more frontier for me to become involved in.
Yeah, well, that's a fascinating story. How wrong you were at that.
But see, you didn't see these things ahead at that time. Bill and I were interested in just having a job. That was our motivation. We didn't have any grandiose ideas of reforming the world or anything. We just wanted to be able to do something that would give us a living.
Yeah.
But also we developed some very conservative policies for that reason, and I don't know whether we would have succeeded in today's venture capital business or not. That wasn't our way of doing things.
Yes. Well, I noticed that a good deal of your your capital has been self-generated through the years, which
actually,
is a different way of doing business today.
Well, it's all been self-generated, with this exception. We do sell stock to our employees. They have the opportunity to buy stock at 25% below the market, and they put $50 or $75 million a year of their own money into company stock. So we have generated some capital from that. But we have no long-term debt, and we've never sold equity for the reason we've been able to generate enough funds to finance a growth of in excess of 20% a year with our own resources.
Yeah, so you rest on a very solid foundation financially.
Well, that goes back, you see, to our sort of depression area philosophy, which is not exactly what we're seeing around the country today.
No, things have changed. In addition to all of these contributions, though, of course, I can remember your contributions when you actually agreed to go back and serve as Deputy Secretary of Defense, and then also your activities in technical societies and your activities in the education field. I note that you were on the board of National Merit scholarships. My son happens to be in the first class in 1956 of this, and this has been I know it's been a tremendous influence on education in helping to encourage our top people.
Well, I don't know why. I can't explain exactly how I began to become interested in doing some of these outside things, but somewhere along the line I became interested in education and decided to run for the school board here in Palo Alto.
Oh, that's it.
Which, I don't know whether you never knew that.
I didn't know that.
Well, I ran for the school board, and I guess it was in 1946 or 47, I can't remember the date, and much to my amazement, I won, served on the school board for quite a few years. And then I was invited to go on the board of trustees of Stanford University in the early 1950s. And that was also a very interesting experience because Stanford had just embarked on a plan to develop their lands and provide a broader base to establish the industrial park here and the shopping center. And at that time, the board was quite small, and it was a lot of fun to work with the other trustees on those problems in those days.
Yes, that must have been a very satisfying thing to work there, because education, of course, is the hope of the future. Unfortunately, there's some of these policies which don't really give impetus to having our best people advance as far as they can.
Well, I think that education did have a rather serious setback from the late 1960s to the early 1970s, and it came about because of the concern about social problems and equal opportunities and so forth, which were perfectly legitimate concerns. But they opened up the admission to the universities and reduced the requirements for graduation from high school and so forth. And in a sense, our educational system became as much an institution for social reform as it was an institution for education. And I think our educational capability was suffered as a result of that. I think that's been understood and recognized now. And there are a number of things being done which I think will improve the situation. And the first problem is to recognize what the problem is, and then you can do something about it.
Yes, I am reminded of a very famous Stanford professor, Terman. I'm not sure whether he's related to psychology.
It's his father.
It's his father who did this work on the 1,500 gifted children, which I followed for decades. I think we used to publish every decade, and it is amazing how the encouragement of these gifted children led to such tremendous contributions.
Well, it's interesting to look at the young people, we hire about 1,000 young people a year from various universities across the country. As a result of having done this for a number of years and the general interest in the electronics field these days, we are able to select some of the best people from all these schools. And I must say that the young people today are just as bright, and if not brighter, than they ever were. So I don't think our system has suffered perhaps as much as some people might indicate. At least we're educating a lot of very fine, challenging young people.
Yes, I'm very amazed in talking to some of the young people, particularly in the computer field, how they have a tremendous grasp of such a complicated system.
Well, of course, these our fund of knowledge is growing, and the students have the benefit of there's more things to know today than there were when we were in school.
Well, this is it's very, very reassuring to hear you with your faith in the future, you might say, of our bright young people that are coming along. And,
well, I think actually the opportunities today are just as good as they were when Bill and I started, and perhaps even better. So I don't think there's anything to worry about from that standpoint.
Well, very good. Well, I was wondering, do you have any other points of philosophy that you might leave with us today? This has been a marvelous exposition of how your company got started and the contributions.
Well, there's only one other thing I'd like to comment on. During this period that our company has been developing, we have also become extensively involved on an international basis, as you know.
Oh, yeah.
In fact, roughly half of our business is outside the United States. It varies a little bit depending upon the economy in other parts of the world. And I think it's important to point out that the world economy is becoming much more interdependent than it was in the past. And if a company such as ours is going to be successful, we have to look at the worldwide competition, not just competition here in the United States. And for that reason, we've been concerned about the Japanese competition, and I've been particularly interested in that this last year because I've been involved in a member of the United States-Japan Advisory Commission, which we're working with a small group of Japanese counterparts to hopefully make some recommendations on how we can maintain a good working relationship between the United States and Japan. And I think we're very fortunate that the free world is developing in a very constructive way, but in high technology industry, the Europeans are falling behind a little bit. They're all trying to figure out how to catch up now. We had a visit earlier this year, the Queen of England, and just the other day, the King of Sweden, and so all of the European countries are sending some of their distinguished people over here to try and see what we're doing here in Silicon Valley, as a matter of fact.
Well, it's very interesting to see that these heads of states come right here to find out, you might say, international relationships there.
Well, it is an interesting thing, and of course, this is really Fred Terman is really the person more responsible for this development than anyone else, and I've indicated how important he was in helping Bill and me in our business. Many of his proteges are also running other businesses in this area, and that whole contribution that he began really when he was in his early days as a professor here at Stanford, as I've indicated, kind of set the groundwork for that. And then when he came back at the end, after the war, from his work at the Radio Research Laboratory in Harvard, he continued to work on that prospect and encourage companies to locate out here, and it's just built up over the years until now it's a tremendous development, as you see here today.
Yeah. as I say, with internationally, it is known as the center of this type of activity. Well, Mr. Packard, I certainly want to express our appreciation for the contribution you've just made to this series.